Yeah, so hi everyone. Uh, Good morning to all. Today I'm going to discuss, give just an introduction about the high voltage engineering, which is uh, a subject which generally comes in the fourth year of electrical engineering. So, what is the concept of high voltage engineering and why we should study this subject? Uh, I'm going to just give you some issues which involve in high voltage engineering and why it is and how to get over through that. So, high voltage engineering, there is a topic there called as over voltage due to switching surges, system faults, and other abnormal conditions. So, over voltage, what is this? And we are going to see now. So before going for that, all of us has to understand why do we go for high voltage transmission and distribution. So the picture which is on screen describes that entire power system in one picture. So if you observe the picture, what we have here is a power plant. There is it can be a thermal power plant or any kind of power plant like hydro or solar, whatever you think. So this is the at left extreme end in this picture. We have a power plant which generates a voltage of 12 kV. We have a big alternators or generators inside, so which is generating a 12 kV of voltage. But when we see at the other end, at the consumer end, that is the consumers like you and me, we get in Indian standards, it will be like 230 volts or 240 volts. So the voltage getting generated at the power station is 12 kV kilovolts, that is 12,000 volts. And what we get in our home is 240 volts or 230 volts. And in between, if you observe, we have this 12 kV which is getting generated at the power station is stepped up to very high voltage value by using a step up transformer. Just beside any power station, we'll have something called as step up transformer where the voltage value, voltage level will be stepped up to a very high value like 12 kV to 400 kV. So 400 kV is a very high voltage. That is why the name came high voltage engineering. So why should we do that? Why can't we just transmit 12 kV as it is and step down at our premises? Why should we step up to very high voltage and transmit that over long distances through the overhead transmission lines? And then why should we step down? So the reason behind this is very simple. So we know the basic formula for power delivered. Okay, power consumption. We know the formula from the basic laws of electricity. P is equal to V into I. All of us know this. This is the equation for power. Voltage into current traveled. Okay. So here, if you think what is this P means, P is the power, that is the load. How many megawatts? There may be thousands and lakhs of houses in the city. So when we take the power consumption of all the houses combinedly, it will come in megawatts. Okay, it will come in megawatts of range. Each house you can think like 1 kilowatts or something. You'll have fans, refrigerators, motors, all those loads, right? So even if you think each house take it as 1 kilowatt, there may be thousands and lakhs of houses. The value that comes power to be delivered to the city is in megawatts. So that is a fixed one. You can think, of course, it varies, depends on the time duration in the day, like maximum demand, maximum peak load, and normal load, all those things. So for time being, if you assume this P is a fixed one, the maximum load we can offer to the power system is megawatts. And if you think this V, if it is smaller, like if I transmit on 12 kV range, the I will be very high. To balance this is constant. Megawatts is a fixed load for entire city. Now the only variables here is V into I. The point is, if I increase V to a very high value, I can decrease the value of current that is being transmitted on the transmission line. So why should I decrease the current? Why should I increase the voltage so that I can decrease the current? Why should I do that? The question arises. So to understand that, again, if we see the one more formula for power, power is also given by the formula as I square R. I square R. That is, there is a transmission line. This is the transmission line. It will have some resistance or impedance because of its dimensions, and the current I is getting passed in that. Now we have something called as copper losses. Okay, we call this as copper losses. Whenever some current passes through a conductor, the conductor gets heated up because of this loss, copper loss. That is, its formula is given as P is equal to I square R. So if we think that if I can reduce the current value by increasing the voltage to very high value, I can minimize this factor. If this I is very high, copper loss will be very high. I square term, it is a nonlinear term. If I is high, I square will be very high. So there is this I current value will be high only when the voltage is low. So, but I should not allow that. So, for that reason, if I increase V to a very high value, I can decrease I to a very low value so that this copper loss can be minimized. That is, heating of conductors can be minimized, and the size of the conductor. Main point here is the size of the conductors used for transmission of power is minimized. Size minimized by going for this thing. If I don't follow this high voltage thing, I will have to use to satisfy the same power delivery. I should have to use big conductors, because current value, if current value is high, to withstand that large current value, to withstand that heat getting generated, I square R losses generated, I will have to use very thick conductors and very big sized conductors for the transmission of power, which is not feasible practically because of mechanical constraints, sag, and all those things. So the reason behind going for high voltage is reduce the minimize the current value so that I can use the smaller conductors. Okay. So okay, fine. This is the system. But if everything goes fine, it is okay. But what is the trouble here is, while this transmission is happening, we will have lot of various equipments, very costly equipments in these power systems. Like we have generator, big alternators in the power station, step up transformer, step down transformers, uh, insulators on the transmission overhead, that is cross armed towers, and a lot of things, equipments are there. So if we see that this is a simple power plant, thermal power plant, you have generators inside. Beside that, we have a big step up transformer which is stepping up the voltage and taking the current through the transmission line and going to the cities. And so we have very costly equipments installed for generation and transmission of power, like solar plants, big transformers, that is step up transformers, and overhead transmission lines. In that, we have insulators, suspended insulators, a lot of cables involved. That is, and a lot of protection equipments also there in the substations, like. bushings. A lot of things are involved in the system. Okay, step down transformers, current transformers. So now, then what's the problem? If everything goes fine, is everything is okay? But the problem is the natural calamities. So even though we think that our system is very well designed, there are some cases which by nature some kind of over voltages will happen in our power systems. That is, for example, we have designed our system for 400 kV, but and that is our power system, that is transmission and distribution system, can withstand up to 400 kV or maximum 450 kV. If it goes beyond that, uh, entire system will get spoiled out and everything will burn out. So we will design keeping in mind that it can go up to 450. But in the physical situations, because of the natural things that appear in the atmosphere, like as shown in the figure, lightning may happen in the rainy seasons. Lightning is the thing which will generate very high voltages, like thousands of kilovolts from the sky, and large currents will pass from the sky, rupturing the air between and reaches the earth. So while that process is happening, that large currents may come and hit our transmission towers. So entire it may cause damage to the entire power transmission system. It may burn out our all the cables and all those things, our transformers. That large currents may travel to the next level of stage. It can burn out the transformer. It can burn out all the equipments in the series path of that. So one thing is we have to protect our devices through this natural calamities. Okay. So one thing is that problem, and the other thing is we have something called as switching surge. Switching. So generally, even though it is not naturally uh, by nature, by willingness, we sometimes we may want to change over the switches. That is, we may want to connect one area to one power plant, and another area to another power plant, and we do a lot of switchings between the power plants and the consumer ends. So when we are doing that switching operations, like opening and closing of switches, connecting the one area to one power plant or switching over to another power plant, we do some switching operations. So while doing that switching operation, suddenly the switch opens and closes. There will be some kind of flashovers that happens in the power systems. As you can see in the picture, this is called as flashover. A large flame kind of thing, arc kind of thing will happen, and the voltage which was going smoothly, voltage profile which was going smoothly until then, like a pure sine wave, now suddenly gets disturbed, and suddenly a large, a sharp, steep voltage profile will happen, like the one as I show in this graph. So actually, our voltage will be like a sine wave with 50 hertz of frequency, and because of this lightning or surges, suddenly a spike kind of thing will happen. This is a spike. A sudden rise of voltage will happen. This we called as surge. Okay. This surge is because of lightning. So we have two types of possibilities for the surges. One is because of lightning, and one is because of the switching operations. Compared to lightning surges, these switching operations may be little bit less harmful compared to the lightning. So as you can see in the picture, in the graph shown, uh, the surges that is shown because of the switching operations is lower, but the surge which is shown for because of lightning is very high. Okay. So anyway, we can manage these small surges by giving some good installations for our systems. But managing these lightning surges is very difficult task. We have to protect our all our equipments from this lightning uh, voltages, the large currents due to the lightning. So there are various mechanisms to deal with to protect our equipments. So this is the main reason why we are studying this subject. So what are those mechanisms? How do we protect our systems? How do we test our systems before installing? That is, whether it can withstand this kind of voltages and currents in the factory. How can we do that? All these things will be discussed in this subject. So I hope I make you just a give introduction of what is for we study this subject and what is the reason behind this. So thank you very much for patient listening, and I hope I'll share a lot of information in the further videos. Thank you.